Hey folks, imagine you're a pigeon, just cruising above Hiroshima on the morning of August 6, 1945. You've spent your life dodging hawks and snatching breadcrumbs, and today feels like any other. Then, out of nowhere, the sky goes blinding white. Your feathers singe, there's a thunderous roar in your ears, and debris pelts down like an angry flock of crows. You spiral through a cloud of searing heat and ash, heart-hammering, wondering if you just flew into the world's worst flash mob. 1 second you're free, the next everything you know is gone. That's the raw power of an atomic bomb. So how does it work? At its core is nuclear fission, splitting an atom's nucleus, which is just the heavy center made of protons, positively charged particles, and neutrons, neutral particles. Picture an atom as a tiny solar system with electrons orbiting around that nucleus. Some atoms, like uranium-235 or plutonium-239, are unstable, kind of like a wobbly table that needs just one more nudge to collapse. When you fling a free neutron at that nucleus, it shatters into 2 smaller pieces, sprays out more neutrons, and releases a burst of energy. Imagine hitting a piñata that instantly spawns a dozen more piñatas, only way less fun and nobody's singing happy birthday. Those extra neutrons then slam into other wobblier atoms, splitting those too, and pretty soon you've got a runaway chain reaction, each split triggering more splits in an exponential cascade. In a nuclear reactor, engineers slow that down using control rods, materials that soak up neutrons, so you only boil water to turn turbines. In a bomb, they pull all the safety plugs and let it run wild until the entire pile of material releases its energy in a fraction of a millionth of a second, creating a fireball that makes your morning coffee jealous. But you can't just sprinkle a bit of uranium on the ground and expect fireworks. You need enough of that unstable stuff so neutrons don't escape before they cause more splits. That threshold is called critical mass, the tipping point between a harmless fizzle and total devastation. It's like making marshmallows, too few, and they're just sad, stale puffs, just enough, and you get a gooey roast. Except here, nobody's eating anything afterward. Back in World War II, the US built 2 bomb designs that each reached that tipping point in a different way. The first, Little Boy, dropped on Hiroshima, was basically a giant rifle barrel. 2 subcritical lumps of uranium were shot together at high speed, instantly forming a supercritical mass and igniting the chain reaction. No scope necessary, but definitely not OSHA approved. The second, Fat Man, dropped on Nagasaki, wrapped a plutonium core in conventional explosives. When those charges detonated in perfect sync, engineers used tiny exploding bridge wire detonators to fire dozens of lenses within microseconds. They squeezed or imploded, the core inward until it went kaboom. If even one charge misfired, the whole thing would fizzle. Imagine a cake recipe where missing 1 egg turns it into sad pancake. The moment fission goes critical, temperatures leap into the tens of millions of degrees, hotter than the surface of the sun, forming that blinding fireball that expands faster than you can blink. The expanding fireball drives a shockwave, a sudden wall of crushing air pressure that flattens buildings, flips cars, and can even peel skin off flesh like a gross, overzealous banana peeler. Almost as immediate are gamma rays and rushing neutrons, high-energy radiation that damages cells faster than binge-watching horror movies. Then there's fallout, radioactive dust that drifts back down, contaminating everything in its path and making cleanup crews wish they'd chosen a less hazardous career. We measure bomb power in kilotons or megatons of TNT equivalent. Little Boy was roughly 15 kilotons, meaning it packed as much punch as 15,000 tons of TNT. By contrast, the Soviet Tsar Bomba tested in 1961 clocked in at nearly 50 megatons, over 3,000 times Hiroshima. That's like using a sledgehammer to kill an ant, except the sledgehammer is the size of a mountain, and the ant is an entire city. Dropping these devices is more complicated than tossing a rock. Most aerial bombs use parachutes or stabilizing fins to slow their fall and ensure detonation at the ideal altitude, buying the delivery plane a few precious seconds to escape. Today, delivery options include intercontinental ballistic missiles launched from silos, submarines, or even stealth bombers, basically the James Bond versions, guided with GPS-style precision so a warhead can hit a hardened underground bunker instead of flattening your aunt's souvenir shop. After World War II, the US and Soviet Union raced into the Cold War nuclear arms buildup, deploying missiles on land, in the air, and at sea, the so-called nuclear triad, designed to guarantee retaliation even if 1 or 2 legs were wiped out. At their peak, each superpower held tens of thousands of warheads. That's a lot of just-in-case insurance policies. Since then, treaties like START and New START have slashed deployed arsenals, but thousands of weapons still sit in active or reserve status around the world. Britain, France, China, India, Pakistan, North Korea, and almost certainly Israel all have nukes too, so it's not exactly an exclusive club anymore. Proliferation worries keep international agencies like the IAEA busy monitoring uranium enrichment and plutonium reprocessing, trying to catch any sneaky bomb programs before they go live. Accidents have shown how fragile safety can be. In 1961, a B-52 broke apart over North Carolina carrying 2 nuclear bombs. One's parachute opened and it settled harmlessly, but the other came close to arming itself. Only a single safety switch saved the day. Imagine almost accidentally ordering a 4-course dinner, but with nuclear annihilation as the main course. Looking ahead, scientists and engineers work on nuclear forensics, tracing fissile material back to its origin if a device ever detonates, and improve detection networks to catch clandestine tests. Meanwhile, civilian nuclear power is evolving too, with next-generation reactors that shut themselves down passively if something goes wrong. Kind of like your laptop's battery saver kicking in before a meltdown, except this really matters. Understanding atomic bombs isn't just morbid curiosity. It's critical for crafting smart policy, building safer reactors, and developing defenses. It shows how a single scientific breakthrough can give us both devastating weapons and low-carbon energy, depending on how we choose to use it. That's the full picture. From that pigeon's eye horror in 1945, through explosive science, Cold War arsenals, modern miniaturization, and efforts to keep the genie in the bottle. If you survived this without your brain going super critical, go ahead and smash that like button and hit subscribe for more wild science breakdowns. Thanks for sticking around, stay curious, and definitely not radioactive.